All right, so this is probably going to be our last video for the probability unit. We do have one, it's not a new topic, it's a merging of two topics we've already covered. We're going to do a couple of examples of that. Then I'm probably just going to randomly pick a few extra problems to do. I'm going to put up a list to remind you what's going to be on the probability test. So for homework, pretty much this should be the only thing you have not done. On worksheet 1, the chapter 33 pages, at the very end, you'll see how I hand wrote some extra problems. That is definitely what you want to practice, and then start reviewing everything and redoing everything. So when you pull out this page, probably from the last video, that's what I mean by the handwritten ones. Okay. All right, so we're going to, you don't have to get worksheet 1 out, but we're going to revisit one of the problems on there. And we're particularly doing part D. This was the problem that was talking about houses and American homes and whether they had lots of cars or not. So the probability that some family has lots of cars was 17%. That was given in the problem. So of course we know that not having lots of cars is 83%. And they said that there were 3 houses. And the question in part D was, what's the probability one has lots of cars? So at the time when you were doing this problem, you may have been a little confused and had to look at the answer key. We had done a few of these in lecture. Remember this, it didn't say the pink house has lots of cars or the Watsons have lots of cars. It says one of them has lots of cars. Well, I don't know which one. So you would have had to come and kind of think about your dashes and say, well, did you mean the first house has lots of cars and the other 2 don't? Or did you mean the second house had lots of cars and those 2 don't? Or did you mean that the third house has lots of cars and the other 2 don't? And so then you could have gone and put your 0.17, 0.83. We never did this as part of the video, so that's why I'm writing out every single step. Now hopefully you recognize that those are the same 3 quantities, right? It's like x plus x plus x. Repeated addition is multiplication. And that is why on my answer key, you'll see that I wrote it like that. And of course, 0.83 twice is squared. And I guess that turns out to be 0.3514. So that's the way the problem was designed when I assigned it, right? And I knew that I had done something very similar in lecture with Jeannie remembering and forgetting, so I figured you could pull out your notes. And coming up that there were 3 of them really isn't that hard, right? But now we can do this a different way, because the idea is there are 3 houses and we need to figure out how many ways to pick one of those houses. One has lots of cars. That's a combination. See, because here's the thing. Look at this. This is how many ways. And we had to figure out there were 3 different scenarios happening, right? And what does this represent? The probability of one of the ways, right? Like if it had said the red house has lots of cars, I would have just written this. What does the probability of one of them look like? So this number of ways, that's the hard piece. That's the one that we had to sit here and make sure that we had written every possible scenario, right? That is the combination. So I want to leave that there. Instead of having to figure out that there were 3 of them, you can now come back, since we learned combinations in the last video, you can do the problem like this. Same problem. understanding that it's a combination. This will tell you how many ways. And then you do have to think about, well, one has lots of cars, meaning the other two don't. This is that probability of one way. So that combination, 3 combination 1, if you put that into your calculator or if you use the formula, this is going to give you 3. We already knew that, right? I'm just showing you a different way to do the problem. This was easy enough that you could do it the long way, or you could do it the combination way. So of course the same answer. So at this point, for this particular problem, you might say, oh, it's easy enough just to do those 3. I'll just do it this way. I don't like combinations. Yes, but very often it can be 100 different ways or 1,000 different ways. And there's no way you're going off to the side of your paper to figure out that many. This one only had 3. It was easy. So let's do a bigger problem. I'm just going to make up one. Oh, well, I had done something with meal plans. You don't have to, it's not important to pull out the notes, but we had said the probability that a JMU student has a meal plan is 40%, and we were going to ask the next 20 students. We had done a few pieces of this setup in some other video. Piece we want to do now, well, let me do this. What's the probability John, Sue, and Mary, well, maybe I should say only John, Sue, and Mary. I was going to put the only in the wrong spot. Only John, Sue, and Mary have a meal plan. See, I named them. I'm not confused as to which 3 people you're talking about. So those 3 people have a meal plan. Remember though, we look at our exponents, we haven't taken care of all 20 students. Oh yeah, so that means the other 17 people, whatever their names are, do not have a meal plan. Gives you one more chance to practice scientific notation. To 4 decimal places, this is approximately 0. So that's that precise order. Don't overcomplicate it. We like these. They're quick and easy. But let's switch it up now. What about if the problem says only 3 people have a meal plan? Well, wait, I don't know which 3 people you're talking about. Is it John, Sue, and Mary? Is it Sue, Mary, and Chloe? Is it Chloe, Mary, and John? Is it Chloe, Thomas, and Zoe? Is it Zoe, Mary, and Thomas? I mean, you'd have to go through all of the different ways. There's no way you're going to do that on the side of your paper. Speaking of which, I'll tell you how many it would be. Just to convince you you're not doing this the long way. There's 1,140, so that's not an option. But to understand that you would have to figure out all the different ways to grab 3 people out of the 20. That's that 20 combination 3. That would tell you how many ways. How many of these things would we be adding up? Times 3 people having it, 17 people not having it. So you'll see, of course, that this part is the same, but there are multiples. We would have this for John, Sue, and Mary. We'd have this again for Sue, Mary, and Thomas. We'd have this again for Mary, Sue, and Chloe, just like I did on the last problem. So you've got to figure out what 20 combination 3 in your calculator is. Then you're going to multiply it by that, and you will get maybe I should make sure you're figuring out what 20 combination 3 correctly is. It's 1140 times 0.4 cubed times 0.6 to the 17th. 0.01234 is the answer. We'll probably do one more of these before we end this video, but right now I just wanted to show you two more real life times in real life that counting principles, permutations, combinations, the counting principle, whatever, actually just organically came up. Just so you don't think it's just stuff we learn in a textbook and we never apply it. Super Bowl 2019, the one a year and a half ago. I don't think it was 2.5 years ago, but it doesn't matter. There was a Pringles commercial. If we were in the classroom right now, I'd probably pull it up on YouTube. And it was about, apparently, they want you to buy Pringles, right? The commercial was about stacking Pringles. Like you watch the person pick out 3 Pringles and put them in a little stack and then take a bite. And I guess you're supposed to use 3 different flavors, makes it more interesting or something. Don't eat Pringles. I wasn't that interested in Pringles. But at the very end, in the background, Alexa, the little technology thing, says something like, oh, there's 318,000 flavor combos. So they were talking about stacks. And then Alexa in the background at the very end says something about 318,000 flavor combos. So I remember I immediately turned to my daughter. I'm like, I wonder if anybody ran the math or if they just made up a number. And this is one that people are having a field day with it on the internet, trying to figure out what assumptions did Pringles use. So that's where it got really confusing. Myself included, most of us were coming up with a lot of different numbers besides that. I tried to count how many flavors of Pringles they showed in the commercial, but I think some of them were duplicates anyway. We were also wondering, could you use repeats? How many flavors are you talking about? And define a stack. In the commercial, they were putting them in stacks of 3. So eventually, I think a few people were able to get a statement from Pringles because, we're interested in math and people were emailing Pringles. So this is what Pringles said was their assumption when they programmed Alexa to say that number. You would never have known this from watching the commercial. So this is what Pringles said. They said they had 25 flavors, and they defined a stack as 2, 3, or 4 Pringles at a time. So they did not specify that, or they seemed to indicate different flavors. That they weren't just stacking 3 plain ones, because I guess that wouldn't mix flavors, right? So that kind of makes sense. But it was interesting. They only showed the stack of 3 on the commercial, but Pringles said to get that number, they used stacks of 2, 3, or 4. So this is a perfect combination problem, because Pringles also did not indicate that they cared which one was stacked on the bottom, which one was stacked in the middle, and which one was stacked on top. And that kind of makes sense, because by the time you take a bite with your mouth, it's all getting mixed up in your mouth anyway. So that all seems reasonable. Now, if you go with what seems reasonable, then we're doing how many ways to pick 2 flavors out of the 25. And, you're just picking one of the barbecue and one of the salt and vinegar or something. And 25, choose 3. And then for the stack of 4, you need to pick 4 out of the 25, right? So this is what some of us started doing when we read the email from Pringles. And we were not getting 318,000. We were getting 15,000. So just trying to show you advertising. If you actually do a permutation, for each one, thinking, okay, let's just talk about the stack of 2. You know, which flavor am I going to put first? Which flavor am I going to put, sorry, you can't see that, second, right? 25 times 24. Or this guy would be 25 times 24 times 23. This guy's 25, 24, 23, 22, right? You actually do end up with exactly 318,000. So even though the email from Pringles didn't specify that they cared about the order, we all figured out that that is what they did. But again, think about it. Who really cares? If you put barbecue on top of plain and you stick that in your mouth, or if you put plain on top of barbecue and you put that in your mouth, I'm pretty sure you're not going to be able to tell a difference. But I suppose foodie people can argue with me that the one that's reaching the palate of your mouth will have a different sensation than the one that's sitting on your tongue. You see how you can really overthink this stuff? But you have to always understand, what assumptions did the company make? So, no, technically they were not lying. I have an issue with that they cared about order, but that is where they got their 318,000 flavor combos from. All right. So, one other problem. Let's say you're taking a multiple choice test and there's a particular question and it's A through E, A, B, C, D, E. But don't you hate when professors do the pick all that apply? It is so hard to get those questions correct. So we want to figure out how many ways to actually answer a question like that. So to be honest, for the first 2 years, I did this problem in 207. I'm going to show you how I did it. It was only a couple months ago that suddenly I realized there's a much easier way to do it. So as much as I work with probability and statistics, the more you work with it, the more insights and connections you'll find that you make. So, okay, I'm like, wow, pick all that apply. Well, maybe I just want to pick one, but I don't know if it's A, B, C, D, or E, right? So 5 combination 1, of course, gives me 5. Because I could have filled in A, or B, or C, or D, or E. Just one of them, right? Well, what about if the professor made 2 of them the right answer? Well, which 2? A, B, A, C, A, D, B, D, which 2? That's a combination. Because, of course, when you're filling in the bubbles on a Scantron, they don't care which one you fill in first, right? They just care that you filled in B and C or something. So that gives you 10. Well, maybe your professor had programmed it where 3 of the choices were correct. So 5 combination 3 is 10. What about if there had been 4 of them that were correct? That gives you a 5. And maybe all of them were correct, right? I think you don't have to do a combination on that. I'm just trying to show you 5 combination 5, of course, is 1. There's only one way to fill in all 5 bubbles. So that gives you 31. The only case we didn't do was not filling in anything, because you know that's not the right answer. That's leaving a question blank, right? So let me tell you the real life of this. One of my daughters had a roommate. I think she graduated with a 4.0. Extremely bright girl. But there was one question on one of her biology tests. She truly said she had no idea. She couldn't even narrow it down at all. And it was a pick all that apply. And according to her, she just randomly filled in some bubbles. And she actually got it correct. She knew my daughter was good in math, so she ended up texting her. She's like, I'm pretty sure that was a small probability. I can't believe that I actually got it right. Yes, the probability, if she truly knew nothing, the probability of her getting it correct is 1 out of 31, which of course is very small. I'm going to get you the exact number. Yeah, 3.22% chance that just from randomly guessing she got it right. So she was lucky that day. So combination fits beautifully to what we're doing. It was just a couple months ago that I realized, wait a minute. Remember that trick that we talked about, how to figure out how many types of pizza by going topping by topping and just saying, do I want it or not? A yes, no type thing. Let's do this a different way because it's actually a whole lot quicker. It's not going to be as quick since I'm going to explain it, but you know, she had A, B, C, D, E. She had to figure out if she was going to fill in that bubble, if she was going to fill in that bubble, if she was going to fill in that bubble, or that bubble. So you can think about it as she looked at A, she's like, do I want to fill it in or not? There's 2 ways. Do I want to fill in B's bubble or not? So this is 2 to the 5th, which is 32. Now at this point you might say, wait a minute, I thought you got 31 a second ago. Yes, because think about it. She is not going to leave them all blank. That one way to leave all blank, every student knows you better answer the question, right? Leaving something blank is not the correct answer. So that 32 does include the one way that you don't circle anything, kind of like putting no toppings on your pizza. So at this point, we do have to subtract off that 1 because we know that doesn't make sense. There's your 31. But this is also why I think students, and even myself sometimes, struggle with probability because many times there is more than one technique and the techniques are dramatically different to solve the same problem. We solved this using combinations, then we solved it, I don't know that this technique has a particular way. Of course, it's the counting principle, 2 times 2 times 2, but kind of that trick of do I want it or not, and then making that little tweak at the end. 2 completely different ways to solve the same problem. All right, let's do one more from the topic that this video started with. So this was based off of one of the problems on worksheet 1. You have 8 friends, you're inviting them to a party. The probability that any person accepts is 80%. The question is, what's the probability only 6 people accept? You know, the word only doesn't have to be there. It could say, what's the probability 6 people accept? It's the same thing. I didn't tell you which 6. I didn't name them, right? So, how many ways to grab 6 people from the 8? That's going to tell you how many ways, how many different scenarios satisfy what they asked me. What does one of the scenarios look like? Let's see, 6 people are coming to my party. So I like to actually read this so I don't get bogged down in numbers. I got 6 people, 6 accepting, which means don't forget the other 2 people. I got 2 people declining. There's your exponent of 8. Make sure you took care of everybody. Put that into your calculator, 0.2936. 8 times 7, 4 times... I think there's like 28 ways. So again, nothing that you're going off to the side of your paper and doing. You really need to make sure you understand the combination attached to these probability word problems. And your book does actually do this at the end of chapter 33.2. All right, at this point, I want to make a little list to remind you of just generically all the stuff that we've done in probability. Make sure you don't forget, because you're going to start just studying and practicing problems. I think I'm going to make the list first, and then I'll read it. So the first thing is to make sure you know that worksheet 1, I think it's 6 or 7 pages long. That does not have everything on it, okay? Like, for example, the contingency tables, we had the handout for Zika. I know for a fact that at least 2 of the homework problems I assigned from the book there was one about drug testing, there was one about supporting vouchers for schools or something. So those are the problems that gave you the probabilities, and you had to create the data table. So you won't find any of those on worksheet 1, but you got to make sure you practice them. Reading off of charts, determining probabilities, and then checking for independence. We had 2 handouts: eye color, hair color, politics, gender, and then there was 4 or 5 more on worksheet 1. There was probably even more in the book, I don't know. Remember odds, which is kind of odd, that different form of probability. Can't remember if there's one of those on worksheet 1, but there's definitely some problems in the book and from lecture. Tree diagrams. We were doing condensed. We were labeling the branches. Then we had to multiply the branches to actually get the probabilities. We did examples with and then without replacement, all of that stuff. There's definitely none of those on worksheet 1. So this is coming from your lecture plus the book. Permutations, combinations, all different, counting principles. Sometimes we avoided a permutation, we just used the dash method. Sometimes we use the dash method anyway, like the phone number problem. It was not a permutation or a combination. It was just, let's think through the problem. And then spinners versus dartboards, that would have been back towards the beginning. So all of that stuff. Now, I want to make another comment right here. Well, I'm about to erase, so if you're not ready, pause me, write this down. I remember a year ago I had students getting confused on this. Permutations and combinations, they're two very different things. But what they do have in common, by their very nature, is they use things up, meaning they don't allow for repeats. Like even if I'm putting frames on a wall, 5 times 4 times 3, I can't put the same frame on the wall